In this video, I'll talk about tensors, and in particular, I'll introduce tensors by talking about second-rank tensors. So what are tensors? They are a linear mapping of some sort of spatial property. And so we will use them in particular to talk about directional properties within crystals. An important point about tensors is that they obey certain rules when coordinates are transformed. So let's go through a list. A 0th rank tensor is a scalar. A 1st rank tensor is a vector. It has 3 components. A 2nd rank tensor is a 3x3 matrix. I'll skip 3rd rank and go straight to 4th rank tensor is a 3x3x3x3 array of numbers. Now we'll use a 2nd rank tensor, the 3x3 matrix, to describe both conductivity, stress, and strain. Then I'll talk about a 4th rank tensor, the elastic moduli, or the compliances. So to introduce tensors, I'll talk about conductivity through Ohm's law. Now we have the basic Ohm's law relationship that says the current is proportional to electric field, with the constant of proportionality being the conductivity. Electric field is a vector quantity, the current is a vector. As long as sigma, the conductivity, is a scalar, the current is proportional electric field and perfectly parallel to it. Now, if the material is anisotropic, then current flowing in a particular direction, say the x direction, could have contributions due to electric field in both that direction and all other directions. So we can write a composite effect here in which the current flowing along the x direction has a contribution from the electric field in the x direction, and a contribution from the electric field in the y direction, and from the z direction. The constant of proportionality is indicated in front. We have 3 components there mapping the field direction to the common current direction. Now I can write this in a shorthand notation in which the indice for J is R and the indice for the electric field is S. Think of that as a response for a stimulus S. And sigma RS has coefficients that relate a response direction to a stimulus direction. So there are 3 coordinates for each that would give us a total of 9 different combinations of electric fields and conductivities to current fields. The Einstein convention is illustrated in the equation above because we have 2 repeated indices on the right side of the equation, so that the shorthand notation is exactly the same as the expanded notation above it, in which there are 3 terms because we've summed over the 3 spatial coordinates. We could also write this as a matrix vector operation in which we simply multiply a matrix of values of sigma times the electric field vector to get a current vector. We'll label this thing multiplying the electric field as the conductivity tensor. And written out, it has 9 components as shown here, with indices reflecting the appropriate permutation of x, y, z coordinates, going across for the stimulus and going down for the response. Now, conductivity, either thermal or electrical conductivity, is a 2nd rank tensor. It maps a vector stimulus, the electric field or the temperature gradient, into a vector response, an electric current or a heat flow direction. Stress and strain are also 2nd rank tensors. They provide a map between a direction to either a stress, a force per unit area, or to a displacement. In general, tensors can be symmetric, and a symmetric tensor is one in which permutation of the indices xy to yx in the matrix gives you the same value, or antisymmetric, in which going across the matrix reverses the sign. Now, whether you have a symmetric or antisymmetric tensor is related to thermodynamic or dynamic considerations. Now, stress is symmetric tensor because if it were not, there would be a net torque on the body, and that would lead to acceleration. So for static balance, stress has to be symmetric. Strain is symmetric simply by the method of construction. Conductivity is symmetric based on what are called the reciprocity arguments. And I'll not go into them here, just consider that going in a forwards or backwards should lead to the same value. Now let's talk about the coordinate change associated with tensors, and we'll start with the second rank tensor. In a general case, we have vectors p and q with tensor t mapping between q and p. Now, if we want to switch to a new coordinate system, we'll use a transformation matrix A sub ij, such that in the new coordinate system we have p prime is equal to a linear mapping of q prime, and the linear mapping is through the tensor t prime. Let's list what we know at this point. Well, we know that p prime is related to p by multiplication of a transformation matrix. And we've already pointed out that the inverse transformation, going from p back to p prime, involves using the transpose of the A matrix. So if we write down p prime in terms of p, we have this expression. If we substitute in for p the linear mapping, t times q, then we can replace q with its transformation in terms of q prime. We rearrange the parentheses, and that gives us a quantity in front of q prime that multiplies q prime. So that quantity in front is now the new t prime matrix. And since this is a tensor, it's a t prime tensor. So t prime is 2t by the matrix multiplications of A times t times A transpose. We can write this in subscript notation as follows, where we have, again, the Einstein convention. We have repeated indices on the right side, p and q, and the elements of t prime are obtained by appropriate multiplication twice by A to t. Now, another theorem that's important is that all symmetric second-rank tensors are diagonal in some coordinate system, which we'll call the principal coordinate systems. Thus, there is a coordinate system for electrical conductivity, which has only 3 elements along the diagonal, a sigma 1, sigma 2, and a sigma 3. So application of an electric field along each axis, axis I, gives only a current in the ith direction. So a general tensor has 6 independent coefficients, and in this case now it's reduced to 3 independent coefficients. Well, you don't get anything for nothing. You need 3 Euler angles to describe the coordinate system, so we still have a total of 6 coefficients in the general conductivity tensor. So we'll call this coordinate system with a diagonal only elements the principal coordinates. Typically, we get a principal coordinate tensor if we align the tensor with symmetry elements of the crystal. There's an old insight that the 3 coefficients of the tensor in principal coordinates can be mapped into a representational ellipsoid, in which the axes of the ellipsoid are defined by the 3 conductivities, and the conductivity in an arbitrary direction is the length of the corresponding vector that reaches the surface of the ellipsoid. And I'll not go into that. You can look at Nye for the full discussion. But I want to cover some examples using MATLAB. And in all these examples, the double caret on the right indicates the prompt from MATLAB. What I type first is what you would type, and so I define a matrix, sigma, by putting square brackets to make everything inside of it either vector or matrix. I use semicolons to separate the rows, and I don't put a semicolon at the end of the line because I want MATLAB to print back to me what I thought I did. And MATLAB, when you hit the return, would return this, sigma as a diagonal matrix with elements 1, 2, 3. Now I can define a vector for E with components 1, 2, 3 as shown here. When I hit the return, I would get these 1, 2, 3 as a column vector, and it's a column vector because I put the semicolons in between the numbers. If I'd left a blank, it would have given me a row vector. Now, the general case, the current is equal to the conductivity times the electric field. MATLAB understands how to do the matrix multiplication. I type in sigma times E, and it returns J is equal to 149, as you can see by inspection. Now let's make a transformation matrix in a general direction with Euler angles 40, 50, and 60. There's the transformation matrix that MATLAB would return. Now I can convert my electric field into the primed coordinates by multiplying by A, and that returns this. I can transform my tensor for conductivity by performing the A times sigma times A prime steps. Again, MATLAB understands the appropriate vector and matrix operations. And there's the conductivity matrix in this new coordinate system. So I can now get the current in the primed coordinate system by multiplying my conductivity in the new coordinate system times the electric field in the new coordinate system, and that returns me this vector for JP. Now, just to check that we're doing this right, I type in JPP, and I want to transform it back into the original coordinate system, so I multiply by A prime times JP, and that returns exactly the same J as I had above. Now we can apply symmetry operations to second-rank tensors to obtain the form of the tensor for different classes. Consider first cubic symmetry. And I'm going to create a vector in MATLAB, or a conductivity matrix tensor in MATLAB as shown there, and that will return to me this array of numbers. And you see it has symmetry as you go across the diagonal, and it has a total of 6 independent coefficients. Now I can apply a 90-degree rotation about the z-axis to my conductivity matrix, and after I do that I should obtain a matrix that looks just the same as the original if it is in the cubic class. So here's the appropriate 90-degree rotation. Here is my transformation A times S times A prime, transpose, and there's my new matrix. And you'll notice that some of the elements have been swapped. For instance, the diagonal 1 and 4 in the first matrix now becomes 4 and 1. And you notice that 2 gets mapped into minus 2. Now I also could apply a 90-degree rotation about the x-axis, which would be transformation matrix as defined here, which gives me this combination of A. I multiply A times S times A transpose. That gives me these coefficients in my conductivity tensor. And here you see that the 4 and 6 on the diagonal have been swapped, and we've changed the sign of the off-diagonal elements. Well, examining these three tensors, the original tensor and the tensor obtained by these two 90-degree rotations, it's clear that the only tensor that will satisfy the symmetry of this system is a diagonal tensor in which the diagonal elements are all the same. Thus, conductivity is isotropic for cubic crystals.